I had actually prepared a couple of demos, which it turns out are not possible. So we'll go through the slides. I'll mention where my demos are. If you want to see some live stuff, come to me afterwards and we can go through that. But let's start. I'd like to introduce myself. My name is Craig. I live in Sweden. And I've been working on geospatial analytics for something like 25 years on and off. But the last decade or so has been the most interesting because in that time I've been working for two database companies. Initially, Neo4j. I spent 7.5 years there. 5 years of that, I was the team lead for the Cypher query language. So even though I joined for geospatial analytics, I have experience with query language development. But the last 3.5 years, I've been working at Elastic, and I was employed to work on geospatial analytics, but no surprising, I ended up also working on query languages. So this talk is a bit about query languages. But starting with the question, is Elasticsearch a geospatial database? I'd never really thought about this question until I came to the FOSS4GE in Florence in 2022. This today is now my fifth FOSS4GE, 2 where I did Neo4j, and now 3 where I've talked about Elasticsearch. And the interesting thing about Florence there was we were sponsors. So we had a booth, Jorge and I, and we had people coming and asking questions. And 2 questions really stood out in my mind. One is, are you really open source? This is an open source conference. What are you guys doing here? And I can understand the question because there has been a bit of controversy as to the licensing with Elasticsearch. It was open source in the beginning. Then parts of the license were changed to be source available, not purely open source, due to competition from an unnamed cloud vendor. But over the years, it's turned out that we didn't need to do that. And I have great pleasure to announce a year ago, we have gone back to being pure open source. Elasticsearch is now GPL plus AGPL, genuinely open source. You don't have to ask me anymore if we're open source. So that's a good thing. The second question people were asking in Florence was GIS, geospatial. I thought you guys did logs processing. That's what everyone thought of Elasticsearch. But the fact is we do quite a lot of geospatial stuff. And are we a real GIS or not? Well, I watched the QGIS presentation this morning. Obviously, we're nowhere near doing a massive range of things you can do there, but we do have some cool stuff. But most importantly, I think what was missing in Florence was a nice query language that looked familiar. And that's what the talk today is about. So, quick history of our geospatial support. So in the beginning, we had points, we had an index. It was a geohash prefix tree kind of thing. Worked really naturally on Lucene, which is a text index. So it was easy to do, but obviously it's not ideal. We added analytics and aggregations. Then we did something really important. We built a whole new index. It's a 7-dimensional BKD tree optimized for intersection searches with complex polygons. Well, that was a lot. If you want to know more about it, we can talk offline. But it's a very, very nice index. It performs very well at very large scale for intersections, which is the foundation of almost everything that we do. In 2020 or so, Kibana got some very, very powerful mapping capabilities. This makes it look like a GIS. So I think the GIS checkbox starts to happen over here. When I presented in Florence in 22, what I was presenting was the vector tiles, map vector tiles, and some nice, cool new aggregation work around hexagonal grids, mostly the Uber H3 library. So we have some cool stuff there. But this is, I think, for me, the moment things can change in people's minds. I've avoided presenting in this presentation the old API, the query DSL, which is these giant JSON documents that are very hard to understand. It's an imperative query that you'll send in. Later on, there's some glimpses of it. But what I want to focus on is what we've built and released in 2024, and some of the updates we're doing right now as well. ESQL. What is ESQL? This query on the screen, I've got it popping up a few more times. So you'll see it, and I'll explain it a bit more later. But what you might already notice is this doesn't look that different to SQL. Some of the things there should look familiar if you're used to SQL. And I'm going to guess that pretty much everyone in this room has worked with SQL and geospatial SQL. So the move of Elasticsearch to ESQL is really opening up the door, I think, to people that are coming from those markets. One quick thing I need to say about the name ESQL, that pipe in the middle there is important for two reasons. One is it's not Elastic SQL, it's Elasticsearch, pause, query language. It's easy to think of it as being SQL. It isn't, but it is obviously inspired by SQL. Elasticsearch, query language. I can describe this query language using 5 adjectives: declarative, piped, tabular, vectorized, distributed. Let me start with the first 3 by comparing it to SQL. So here's a slightly simpler query that simply, if you look at the left query there, we're going to read from the airports table. We're going to filter for important airports, scale rank less than 6. We're going to select our columns that we want to display. This basically just reduces the number of columns. And this is important in Elasticsearch because, by the way, we have customers with literally thousands of columns. It's quite insane what we see. So this is quite important. Sort, and finally limit. That process makes a lot of sense. We put the pipe characters in between because it emphasizes the fact that data appears to flow from one section to the other. That's the graphics at the bottom there. You read the data, then you're going to do reducing number of rows, reducing number of columns, sorting, and limiting the final results. That's a natural thing. The SQL query on the right does exactly the same thing. But as you can see from the numbering I've put on those lines, SQL does it in a slightly odd order. They start with the column selection, then they go to where you want to get the data from, then they put in the predicate, the selection, the filter. After that, SQL typically also works in the same order. The truth is, these two queries are doing the same thing, they mean the same thing, and behind the scenes, both of these languages are declarative, meaning the query engine is going to shuffle things, change the order of things in order to try to find the fastest way to get your data. Some of the things are obvious. You can, for example, swap the filter and select. It doesn't matter if you trim columns first or rows first. They mean the same thing, but one might be faster than the other. So both of these languages will change the order of things and do a lot more in order to make things fast. They're both tabular internally, and SQL, of course, the original storage engine will be normally a relational database, which is typically a row-oriented tabular structure. But you start to see people using column-oriented structures. In the case of Elasticsearch, we're a document store with a column store built in. And that column store is very important because it leads to the next thing, vectorized. Inside ESQL, all data flowing through the system is in chunks, which we call blocks, or pages. Each page contains blocks. Blocks are columns. So if the data came from a column store, it streams naturally into this data structure. If the data came from something else, we need to convert it to this data structure. But this data structure is super important. Why are column stores so successful these days? It's because they're fast. If you have a for loop over an array of a primitive type, let's say we've got an azimuth. We've got 1,000 records with 1,000 azimuths, and we want to do a cosine on them. That for loop doing cosines over that array can be optimized down to the CPU or the GPU for very high performance. This is built into modern chips. Whereas if you had it with a row, the row is too complex, the CPU will not be able to handle it, you can't optimize it down. So you must have this. One of the side effects of us building it like this is the beta release of ESQL actually outperformed Elasticsearch itself in the early benchmarks, early last year and the year before. This was quite fun for us, building ESQL, that our beta release was outperforming something that had been optimized for a decade. Of course, the two teams have been, friendly competition, and both sides are getting faster and faster. Last thing about Elasticsearch, it's distributed. Typically, you will build a cluster. If you have a lot of data, you might have hundreds of nodes in that cluster. You can shard your data across that. You can replicate. You can do many things. And a query will come into one node. It will act as a coordinator. It will distribute the query to all the other nodes, try to offload as much of the processing to the data nodes so they work in parallel for performance. And then only the last part, merging the data together, will be done on the coordinator. In addition, we can have multiple clusters. That's what this diagram shows, and we can operate across clusters with different versions of Elasticsearch. All right. Let's go into the geospatial side. I'm going to talk about geospatial in three areas: search, analytics, and other. So let's start with search. Obviously, that's the beginning. That's that query I showed you before. What is it doing? It's looking at the airport index. It's calculating a distance between all the airports and Copenhagen's train station. Then it's doing a filter. We want the important airports only. That's that scale rank filter. We want airports further than 10 kilometers. So we don't have Copenhagen Airport. We want things less than 1,000 kilometers, and we're going to get our airports and sort it by distance. And you can get something like that map view over there. That's a screenshot from Kibana. At the end of the presentation, I have a bunch of slides that show the inner workings of how we make this particular query very, very fast. We probably don't have time for that, but if you want to know the inner workings of ESQL, come to me afterwards, and I'll explain this exact case in detail. Let's start with the standard geospatial query. I should just go back and list these ones. Look at the list over there. We have distance, intersects, disjoint, contains, within. The bottom four are functions that take two geometries. It could be literal geometry or a field from an index or something like that, doesn't matter. We will calculate if they intersect or not and return a Boolean. That means those functions can be directly used in a where clause, if that's how you want to use them. Distance returns a double, so of course you need to do an inequality like we've done in that where clause. Less than, greater than, equals. So if we use intersects, I drew a simple polygon here around Copenhagen. I want to find points of interest. I downloaded some OpenStreetMap data for restaurants and coffee shops and things like that. I want to find them all here inside Copenhagen. That's a little bit messy to type. We have support for parameterization, where you can pass it in your client as a separate variable to make it a little bit cleaner. But of course, what we found is most people really want the distance function. That's how they do it. Polygon intersections are used, but the distance function is the hot one. That, of course, can also be parameterized if you wish. I have demos of all of this. If people want, come to me afterwards and I'll show you. Moving on to analytics. So Elasticsearch classifies analytics into two groups, what we call bucket and metric. In the case of buckets, you're talking about the group by, the by part of an aggregation. We have a stats command, and we must group by something. So, for example, if you filtered all of your events over the last month and you wanted to get the count of events per day, then the by clause would be the day. On day one, you got so many events, on day two, etc. You get a kind of a bar chart. The other type of aggregation is where the aggregation function itself works, like the count itself is an aggregation function, average, sum, max, min, things like that. We've added two geospatial metric aggregation functions, centroid and extent. We have plans for a few others moving forward. But on the bucket side, we have some very interesting stuff. I had to unfortunately say coming soon because it's available in snapshots. You can download snapshots of Elasticsearch. You'll see this tiling support. That's what you see on the right there, where you can group your results into tiles, either geohash, geotile, or geohex, which is the Uber H3 grid. In fact, the screenshot over there is of the H3 grid. So let's look at the aggregation function centroid, for example. Here, I have downloaded data for air quality measurements, many thousands of measurements across the world. And then I wrote a query like this that says, from air quality, filter for valid results, then do the statistics. I want a count, I want an average, and I want a centroid. Then I could put the centroid onto the map, and I've decided to make the size of these icons based on the count of measurements, and the color is based on the quality. It looks like only Greece has bad quality there. Sorry, but no one's from Greece. This is open data, by the way, so whether it is comprehensive or not is up to the data provider. It's from OpenAQ, if you're interested. So this is a case where we used a spatial aggregation function to produce a spatial result. But what is actually quite common is you would use something that doesn't even appear spatial in the query. Look at this. I take the country code and I group by the country code. Grouping by the country code is not geographic, but I can still do statistics, max, min, quality, count, those kinds of statistics, as you would do. If I want to show it on the map, however, I'm going to need something geographic. That last line in that query there is something that we're super excited about because Elasticsearch has for 15 years avoided doing joins. Anyone who's used Elasticsearch knows there are no joins. You have to do joins in the client. And people like Jorge with Kibana have seen that client-side joins. There's pros and cons to that, but really everybody would like to have joins in the database itself. So we have finally, for the first time in 15 years, released joins. The reason we took so long is because if you have a highly distributed database, it's very hard to make joins efficient. So this is a left outer join, but the right-hand index has to be pre-optimized in a certain way, but it works, and we're planning to do much more joins. Here I'm joining on countries, getting the polygons, and then I can color the polygons on the map. Again, the hexagonal aggregations, it's a really, really cool feature. If you download a snapshot, you'll get it. I have a live demo of this if you're interested as well. Moving on to other. So we obviously have done a little bit of additional work over here, but there's not a lot. And we would really like feedback from everyone else, users, potential users. What should we prioritize? Right now, we've got those top 4, which is for creating geometries. Mostly these are going to convert from well-known text into our internal geometry format. We saw that in some of those previous queries. And then a few functions for investigating geometries, envelope, maxx, things like that. But we could quite easily start to add all of the usual functions you would expect for operating on geometries. Like these two, the reason I threw these on here is simply because Jorge's workshop on Monday, he had some nice data demos, and he had to do those two functions in GeoPandas, was it? In Python, before putting it in. And that I thought, well, why don't we just have it in ESQL? So that's something I think we could add very easily, and we'd like to hear very much from everyone else. What do you think is most valuable? So the last part of my talk is the part that I have a nice demo for it, but I can show you just a little bit of this because we probably ran out of time. The inner workings of ESQL. How do we take a nice declarative query like this and make it fast? I did a presentation in Copenhagen a couple of months ago, and for that presentation, I built a visualization tool. Okay, this is that query. Built a visualization tool that tries to visualize that process. This is what's happening. User into query, parse, semantic analysis, planning, etc., etc. And the important part is splitting to the data node versus the coordinator node. So that visualization tool steps through each of these things and shows you all of the steps. And I'll show you just one or two. That's a parsed query. This is the first optimization. Well, this is now semantic analysis, so now that's a valid query. Logical planning. What has happened here, you might realize you had a where clause. It was just one where clause. We've actually split it into two. The first filter was based on the important airports. Then we do the evaluation of the distance, and then we do the where on the distance functions. We've started to already reorder the commands, split them up, join them. The sort and the limit have been merged into a top n. That's because top n is a function that's supported deep down by Lucene, So we know we can make it very, very fast. So we're basically iteratively restructuring the query internally, step by step, with a set of rules. And the important reason for this is we must support every possible query any user has ever imagined and will imagine in future. So we can't have something that just says, optimize that. We have to have a series of rules that's run iteratively. Try to do this, try to do that. And it slowly, iteratively moves the query in a direction that makes it faster, no matter how complex that query is. Finally, we split it into what should go to the data node. This had a sort in it. Sort has to be a global sort. It has to happen on the coordinator on the final results. But if we can get a pre-sort on the data node, it will be faster. So if you look at this, there's a top N in the blue box that's going to the data node, and another top N back in the final coordinator for the final results. So we're going to start to optimize that, and then bang! So this part is a little scary. What's happened here is we've managed to push all of the really heavy-duty stuff down to Lucene. I have a better slide for that. This is what's going to Lucene. It contains scale rank filter. Lucene supports it very well. It contains our distance predicates, which, if you look carefully, have turned into intersects with a circle and disjoint with a circle, which Lucene supports very well. And finally, Lucene even has a sorting by distance built into it. So we've managed to figure out how to get most of the complex stuff in this query all the way down to Lucene, and that makes this thing extremely fast and, as I said before, over insane amounts of data. Right. The last thing here is the data flow. I'll just go to this slide. Every one of these data nodes needs to produce data, stream it to the coordinator, and the coordinator needs to merge it. This particular example has got, there we go, it's an aggregation. We have to keep sums and counts in order to calculate an average. All of the sums and counts are collected on the data node, sent to the coordinator. It calculates the average and provides the final centroid result. And that's a quick summary of the inner workings of ESQL. I think I can open the floor to questions.